Okay, so welcome back to the video. So here's our little definite integral that we're going to tackle, and that's our bounds from 0 to 2012. And then here we have this, what seems to be maybe a little bit of an intimidating integrand, but well, let me first read this out. So we have e to the power cosine of pi times the fractional part of x divided by e to the power cosine of pi times the fractional part of x. Add this with e to the power negative cosine of pi times the fractional part of x. So one might utilize the definition of the fractional part, and that says that for the formula, the fractional part of x is going to equal to x and then subtract the floor of x for our choices for any real number x. So if we want to, we can actually do a little bit of that whole substitution utilizing, the definition of the floor or the fractional part function, put this back in here. And then I guess if we want to go a little crazy with some manipulations. But personally, I think that's, well, I will say that I actually did try for this attempt, but that seemed to not work out in my favor. What we can utilize is the fact that we know that the fractional part of x has a periodicity of 1. So it actually ranges, so the function x as, the linear function x from a range from 0 to 1, there's a discontinuity at every single of those integers. And then the cycle repeats for how the, construction of that graph works. So we can actually utilize that fact to actually rewrite some of this, the integrand. And that's also going to make things a little bit easier for us. And I won't say anymore because I guess the rest of this work is going to be very interesting. So let's actually just jump right in. So as mentioned, the fractional part of x, it has a period of 1. So let me actually write this out. And so with this, it's periodic, but that also has to imply with that our integrand. So I'm not gonna write that function. So I'm just gonna write integrand. The integrand also has a periodicity of period 1 as well. So if we think about it this way, the way we, construct integrals is by definition is, the area of a function underneath the curve. So if we think about this to that definition, that means we are basically saying that if it has a period of 1 and we go from a bound to 0 to 2012, we are basically calculating this same integral from 0 to 1 2012 times. So that would have to say that we can actually write this as a product of 2012 multiplied by the integral from 0 to 1 of our integrand over here. So e to the power cosine of pi fractional of x. So I'm just going to cut to the next clip and then continue forward with the discussion. Now, now that we write this thing out, here's also something we want to notice that as mentioned, the fractional part of x has a period of 1. So we actually take a look at that specifically from our interval from 0 to 1, 1 not inclusive, since again, those are where those discontinuities appear at. What we can say is that that function, the fractional part of x is just going to be the linear function x itself. So let me put that as a little important notion to describe before we can move forward. So I'm going to say for x is in between 0 inclusive and then 1 non-inclusive, then we say that the fractional of x is going to just equal just x. And so with this, now we can actually rewrite things a little bit simple for our integral. So now we're going to disregard the 2012 later and now just focus on writing out, evaluating this integral over here. So we say that this is from 0 to 1. So if I just plug this back in for x for the fractional part, so now we're going to have e to the cosine of pi times x and then divided by, so the same thing, cosine of pi times x. Then add this with e to the negative cosine of pi times x followed by dx. And so from here, we're going to actually do a little bit of a trick and we're actually going to split the bounds up. So what I'm going to do is I'll split this, the first interval from 0 to 1/2 of the same integrand, and then we're going to do this for the same thing from finishing the rest from going from 1/2 to 1. So let me actually fill in the details first. And so from here, now that we actually split the bounds up, so what I'm going to do now is we're actually going to take into our observation specifically for this right side of the integral from 1/2 to 1. And you're going to see why this actually is very interesting to evaluate. So as we can see, we can actually perform ourselves a little use substitution. So that's actually, the standard approach that, generally if you're solving integrals like this, that's probably the first thought in mind that you want to do. So what we'll do is that we're going to let this substitution, we're going to let x equals 1 subtract u So if I just differentiate both sides, so that means dx is going to equal negative du. So now putting this back in, so I guess I should also say, let me put this over here. I'll abbreviate it. I'll say WTE for want to evaluate. Keep that in mind. No, we're not saying WTF. Anyway, so if we actually plug in back our new bounds, so if I plug in 1/2 back into here for x, so that means this is actually going to be 1/2 on the bottom. And if I plug 1 back for x, so that means u will be 0. That's nice since we'll have a negative du, and then I'll flip the integration, but let me actually put this back and forth and then perform the next steps that we need to. So we have e, then cosine of pi, then 1 minus u, all this being divided by e to the power cosine pi 1 minus u, then we just take with the negative, so negative cosine of pi 1 minus u, and then now multiply with a differential du, then we have our new integral, so this will be flip the bounds, and so now the negatives cancel, so we're just left back with the same integrate, just like from the previous above. And so from here, now let's actually notice that we can actually do a little bit of some evaluation with these, the powers of the cosines. So what I can do here, and you can also actually do this in 2 ways. Both ways specifically, you can apply the either the sum / differences of those trig identities input. So what I can do is, you can choose either way you want, but that says that depending on which one you're using, you just want to be careful with the steps. We know that cosine of pi times 1 minus u. So if you just distribute a pi into here, then you can use one of those identities. For one, I'm just actually going to use the summation that says that that's going to equal negative cosine of negative pi u. But we can use the fact that cosine is an even function, so that just gets rid of the negative of the input itself. And so we're just left with negative cosine of pi times u. Okay, and so from here now we actually have a new rewritten integral. So let's see. So we have from 0 to 1/2 again. So 0, 1/2, and so now basically we're just left with now e to the negative cosine of pi times u, and then basically just now this is going to be the same thing, negative cosine of pi times u, and then add this with e to the positive cosine of pi times u and then du. And so with that, again, so that's actually what this comes down to over here. And so what we can do now is you'll notice that they share under the same bounds, and then we can apply some linearity, which is great, because if you notice that, let me actually draw this arrow. So here implies here. And then if I skip the step again, for substitution, so now we can actually combine this together with linearity. So now we have our new integral from 0 to 1/2 of e to the power cosine of pi times x. And don't forget, this is just a dummy variable for 1. So again, this is equal to the same thing, but with a different variable. So this is actually going back to the world of x. So add this with e to the negative cosine of pi times x. All this being divided by e to the power cosine of pi x. Even though it's different, but again, this is addition, under addition, so it's commutative, so it's okay. And then add this with e to the negative cosine of pi x, and then dx. Interestingly, that's nice because these are the same and they both cancel each other out. So we're just left with the integral from 0 to 1/2 of just 1 times dx, which in fact is just equal to just 1/2. And then just like that, we are done. Just take that 1/2, multiply by the 2012, and so therefore 2012 multiplied by 1/2 is going to equal 1006. And just like that, we have computed what is, the integral looks intimidating at first, but it actually comes down to a pretty easy procedure / result. So just like that, yep, that's pretty cool if you ask me.